Hey, what's up, guys? Chung here. So today, let's take a look at this LeetCode problem number 436. Find right interval. Okay, so you're given like a set of intervals, and for each of the interval I, check if there exists an interval j whose start point is bigger than or equal to the i's ending endpoint. And for each of the I here, for each of the interval I, you need to return like the minimum index of the interval j whose like the starting point is greater or equal than the i's ending point. Okay, and if there's no such index interval j whose starting point is greater than the i's ending point, you just put a -1. Okay, so the example one here, right? So the first one is always if you only have one item, there is no other intervals. Okay, so that's why the only thing you have is -1 here. And the example two here, okay. For example, the first one is 3 and 4, and 4 is the target we're trying to looking for, right? Basically, we're trying to see of those among all of those intervals, if there's any intervals whose starting point is greater than 4. But unfortunately, there's no such intervals. That's why the first one is -1. Okay. And now we're checking the 2 and 3 here. So now 3 is our search target. And okay, it happens to be that the 0, the 3 is equal to the equal to 3. That's why we have 0 on the second index, on the second element. So here, now we're at like 1, 2. So the number 2 is our search target, right? And okay, and then we're looking for um, yeah, actually, sorry. So I think the description is a little bit confusing here. So okay, so here's the here's the tricky part. Basically, you need to find among all the intervals, right, whose j is greater than the current I starting point. You need to find the minimum start point, the minimum start point of all the interval j's. Okay, that's why when we are at here, right? That's why when we are at 1 and 2 here, okay, so we're looking for if there's any interval who is greater than 2 here. Now we have two options. We have two candidates, 3, 4, and 2, 3, right? Both 3 and 2 is greater than 2, but since we're looking for the the minimum one, that's why we need this one. That's why we need this interval whose index is 1. That's why we have 1 here, not 0. Okay. Cool. I think, you know, as long as you can understand the description of the problem, the solution shouldn't be that hard to come up with. I mean, uh, the the brute force way is like every time we loop through each of the interval, right? In each of interval, and then we have a target. Okay. So from the target, right, we loop through all the intervals one again from start to the end. Okay. And every time when we find like valid candidates, right, which means that interval's starting point is greater than our target, then we just try to maintain that minimum start point. Okay, and then in the end, we simply return the minimum index of that. Okay, basically while we're maintaining like the current minimum start. Okay, we're maintaining like the minimum start. So every time when we have a valid candidate, we check, okay, if that start is smaller than this minimum start. If it is, then we update our index. Okay, yeah. And in the end, we simply return that minimum index. Okay. Mm, but since there's a like this constraint here, you may assume that the interval's endpoint is always bigger than its starting point, and also none of these intervals have the same start point. Okay. What does this mean? The second one means that if we sort by the start point, right? So basically everything is increasing. So that and it's kind of obvious that we can use the binary search, right, to find the minimum starting point. Okay, and since each of the starting point is unique, we can also build like a hash table, right? With the key is the start point and the value is the index for that starting point, so that later on, after we find the minimum starting point, we can easily find the interval index for that starting point. Okay, so let's try to code these things here. Answer equals to, and then we have an n here. Okay, n is the length intervals here. So like I said, I'm going to create like a starts, uh, like a hash table. Okay, and um, the key is the starting point and the value is the index. So that later on we can use the start point to find the index. So the key is the interval, for I and interval in enumerate. Okay, intervals. Okay, and the key is the starting point, which is the interval, the first element of the intervals, and the value is the index. Okay, that's how we initialize our hash table for the starting point and its index. And then next one is we just need to sort, right? We just need to sort all the starting point. Okay, so basically I'm just have like sorted starts equals to what? Equals to the sorted, same thing here, right? The interval 0 for interval in intervals. Basically I'm using like a shortcut in Python. Basically I'm looping through all the starting point among all the intervals, and then I save them into a list, and then I sort that list so to get the sorted starts. Okay. Now we have a we'll start and end, right, in the intervals. Okay. And what's our target? Basically, our search target is the endpoint. Okay. And we're trying to find the minimum. Okay, the minimum starting point that is greater than our target. Okay, So I'm gonna use the Python's bisect, left to find the index. So the source is this, and we have a target here. So why I'm using a bisect left here? So bisect left means if we have the same value as a target in this like sorted stars list, we're gonna return the index on the left side. So why is that? Let's take a look here. Let's say we have 1, 2, 3, 4, and 5. Okay, and let's say that's our sorted starting point, and our target is 3. Let's say the target is 3 here, and that's our start. That's our start. All the starting point, and we're looking for the 3 here. Okay, so uh, so if we have a 3 here, right? That's the basically if we have 3 here, and we know that's the answer that's the starting point we're looking for. Okay, and the index is 0, 1, 2, 3, and 4. Okay, and when we have like a 3 here, right? So we're gonna return the index on the left side, which is 2. So here the index is 2. It's on the left side. But if we're using a bisect right, and if we have a 3 here, right, if we see the same number as our search target here, instead of 2 here, it will be returning the index on the right side, which will be 3. But that's not the answer we need, because we need 3 here. Okay, so that's why we use a bisect left. Okay, what if let's say we have a not 4, 5. Let's say we have a 7, 7 and 8. Okay, let's say we have 7 and 8, and we're looking for not 3. Let's say we're looking for 5. Okay, so in this case, since there's no same element in this search array here, it doesn't really matter if we use a bisect left or right. It will just always give us 3 here. Give us the position to insert. Basically, this thing returns you the position that you can insert this 5, which in this case it's gonna be 3. Okay, and the 3 is the answer we need. Okay, because we're looking for the answer that's greater than equal greater than 5, which is 7 in this case. Okay, and that's why we choose this bisect left here. How about the minus one? How can we know if there's no such element? Okay. Mm, cool. So let's say we're looking for 9. Okay. So if we're looking for 9 here, there's no such element which is greater than 9 in the array here. So how can we know if there's nothing in the target? There's nothing in the sorted stars that we can find the target position. So in this case, if we have a 9 here, right, the index returning will be like what? 0, 1, 1, 2, 3, 4, 5. It's going to be 5 because as 9, since 9 is greater than all the elements, that's why the insert position for 9 will be of the uh, at the end of the array. Okay, so with that, we can simply do a check here. Basically, if the index we're returning is equal to the n, then we know we couldn't find any starting point that's either equal or greater than the target. Then we simply append -1. Okay, else else we append, okay, so here it's the starts hash table comes into play here. We're gonna have like, let's do a start point. Start point, okay, start point. It's gonna be the starts, sorted starts dot index, okay. So now we have the index. We just use the index to look for the real start point that we need. But with the start point here, we can just use the start point to go back to the starts hash table to find the index for that starting point. Okay, and then we just append that to the answer. And in the end, we simply return the answer. Yeah, I think that's should just work. Oops. Uh, oh, sorry. Sorted. It's a function here. Cool. Submit. Yeah. So it passed. Basically, uh, the first approach, the brute force approach is just to do a nested for loop, which will be n square. But for in our case, right? So let's take, how about the time complexity for this one? Uh, this one is O(n), right? That's O(n). This is n log n, right? Because we sort. How about this one here? Here's n, right? Here's n, and the by select is log n. So in total, it's n log n. That's the time complexity. Space is n. Okay. So basically, we're just using we use the binary search uh, to improve the time complexity from n squared to n log n. Yeah, here. Yeah, I think that's pretty much it is. It's a pretty easy, like I would say it's a easy to medium problem. So it's a good practice, right? It's a good practice for you guys to get familiar with the binary search, right? Both the binary search and maybe the hash table a little bit. Okay, cool. Thank you so much for watching the video, guys, and stay tuned. I'll be seeing you guys soon. Yeah, bye bye.